Watch a large-scale project burn through $20,000, and you'll find a multi-agent system talking to itself in endless loops until it crashes. At the other extreme, a simple script can shatter the second it encounters a single variable it wasn't programmed to expect. These failures reveal a common pattern. Deployments often stall not because of a model's low IQ, but because the architecture of the agent was mismatched to the task. This hierarchy, known as the agent ladder, identifies 5 distinct rungs of autonomy. Based on the classic agent types from Russell and Norvig, each tier exists to solve the specific failure mode of the one directly beneath it. Engineering a reliable system requires the restraint to stop at the lowest viable rung. Climbing higher than necessary adds latency and cost without adding performance. The first rung is the simple reflex. This is the most basic agent form, a fixed map from a perception directly to an action, operating with no memory and no internal state. This pattern runs the logic inside over 800 million digital thermostats and nearly every standard email spam filter. The mechanism is a straight line. There are no loops, just a rigid if-then rule that triggers an action. This speed causes extreme brittleness. Without an internal model, a single unseen input will cause it to take the wrong action, or no action at all. A reflex has no capacity for doubt. In the 2018 Boeing 737 MAX disaster, the MCAS system was hardwired to a fixed rule based on a single sensor. Without a model to question if that sensor was lying, the system acted on faulty data with no way to second-guess its own logic. When an environment is unpredictable, an agent needs the ability to look ahead and evaluate its options before it acts. Rung 2, planning, solves brittleness by unlocking foresight. Instead of a fixed reaction, the agent decomposes a high-level goal into a sequence of subtasks. Modern coding agents like Devon use this to map out a branching tree of thought. By simulating different paths, the agent can choose the most efficient route toward a goal. However, this foresight assumes the real world will behave exactly like the agent's internal map. If a single step has a side effect the plan didn't encode, the entire sequence can suddenly collapse. This leads to combinatorial explosion. Once a plan exceeds roughly 20 steps, the number of possible outcomes grows too large for the system to track, forcing the agent into a loop of constant replanning. To handle long-running tasks, the agent cannot just look forward. It must be able to look backward and recall its own history. Rung 3, the memory-augmented agent, persists data across sessions for historical context. The trade-off is retrieval noise. Irrelevant data causes hallucinations. To impact the real world, Rung 4 is tool using. The agent uses structured function calls to interact with live APIs and code. This pattern enables viral agents like AutoGPT to research and execute tasks autonomously, but it also creates a new failure point, tool hallucination. A single malformed parameter can trigger a cascade of errors that the agent may not be able to self-correct. When a task becomes too large or too complex for a single sequential agent to manage, the architecture must evolve into a coordinated group. The final rung is the multi-agent mesh, where specialized roles operate in parallel. This follows Marvin Minsky's 1986 theory that intelligence emerges not from a single process, but from a society of smaller, coordinated agents. Building a mesh introduces massive coordination overhead. This has led to a split in engineering philosophy. Teams like Cognition often argue for keeping context within a single agent to avoid information loss, while others, like Anthropic, have used parallel sub-agents to scale up broad research tasks. The decision matrix on the right provides the rule for avoiding the over-engineering trap. Match the problem to the lowest rung possible. If the mapping is fixed, use a reflex. If the goal is sequenced, use planning. Jumping to a higher rung than the problem requires is a primary cause of failed deployments. The most effective agents are simply those built with just enough complexity to solve the task at hand. But as we climb these rungs toward higher autonomy, a new problem emerges. How do you reliably test and evaluate an agent whose behavior is no longer predictable by design?